In this presentation, I'll be providing a brief overview of our paper titled ScaleWave, Breaking Through Resource Bottlenecks to Scale Up Serverless Computing at the Edge. This work explores how we can improve the scalability of applications deployed in resource-constrained environments using the same serverless paradigm widely used in the cloud today. Briefly looking at serverless computing allows developers to write small fine-grained function code rather than building large monolithic microservices. Because these functions have a smaller footprint, they allow much faster creation, deletion, replication, and migration times. This makes them inherently more scalable. Meanwhile, the underlying serverless platform manages infrastructure and resources, automatically scaling based on incoming request load. The platform observes this incoming request demand, and when the demand increases, it creates new replicas of function instances, and requests are routed to these instances for being processed. When demand drops, these replicas are destroyed. This abstraction simplifies development and allows applications to scale automatically, which is also known as autoscaling. However, most serverless platforms were designed with the cloud environment in mind, where resources are much more abundant in nature. The edge is fundamentally different in terms of both available resources and workload characteristics. By analyzing our real workload risk, we found that cloud workloads typically have relatively stable demand patterns, while edge workloads are highly bursty and unpredictable. In the data shown here, cloud workloads have a mean to max request ratio of 0.59, while edge workloads have only 0.07. This means edge systems experience sudden spikes far more frequently than cloud systems, and handling these spikes using existing autoscaling strategies would require up to 8 times more redundant resources, which is unrealistic for edge deployments since edge nodes are resource limited compared to the cloud. The fundamental problem does not lie here in the autoscaler's logic of creating new replicas. Instead, the issue arises because the autoscaler is unknowingly tied to implementations that depend heavily on a single resource type. For example, consider a face recognition function which is compute bound and heavily uses the CPU cores. During high demand, autoscaling simply creates more replicas, which inherently means more pressure on the compute resources. In the cloud, this is manageable because additional compute resources can be provisioned easily. However, at the resource constraint edge, compute quickly becomes a hard bottleneck. One resource type, such as the CPU here, becomes fully saturated, meanwhile other resources such as the GPU, network bandwidth, or the memory may still remain underutilized. Yet the system cannot leverage these resources to scale further. This tight coupling between an application's implementation and a single dominant resource type severely limits scalability at the resource constraint edge. This observation leads to our key insight about equivalent implementations, where we ask the question, what if a function had multiple implementation, where each of these implementation relied on different resource profile? So for the same face recognition function, the possible implementation could look like a GPU-based version relying more on the GPU than the CPU, a cloud offloading version that sends the task to the cloud using network bandwidth. So all these different implementations produce the same output, but their resource dependencies differ. We observe such equivalent implementations already exist at the edge today, and some examples include edge to cloud offloading, where compute limited edge node sends tasks to the cloud using the network bandwidth. Similarly, caching systems such as CDN, which rely on memory instead of CPU GPU computation cycles, and hardware specific implementations such as the GPU accelerated versions. However, there is no systematic platform support to orchestrate these implementations, and developer must build ad hoc solutions such as custom resource monitoring, fallback logic between implementations, and manual switching for policies. These approaches introduce significant developer burden, while existing serverless platforms do not support auto scaling across multiple implementations of the same function today. This represents a missed opportunity to utilize available resources efficiently at the edge. So our goal here is to address this opportunity, and we aim to enable systematic orchestration of equivalent implementations. Rather than reinventing the wheel, we try to leverage existing serverless platforms and then their auto-scaling mechanisms too. However, achieving this introduces three key challenges. Firstly, the design must remain compatible with existing serverless platforms without modifying their internal mechanisms. Secondly, the orchestration policy must maximize throughput while still maintaining acceptable latencies, and developers should have an easy-to-use interface similar to existing serverless systems. This introduces to our design of ScaleWave, which is designed to address this all challenges. It provides an orchestration layer on top of existing serverless platforms, specifically targeting the edge environments. The main idea here is simple. Instead of scaling a simple single implementation, ScaleWave supports multiple equivalent implementations and proactively distributes the incoming traffic across them. Traffic distribution is dynamically adjusted based on system load, available resources, and the performance of the implementation that is observed at runtime. The underlying serverless platform continues to autoscale normally based on the incoming traffic. The ScaleWave requires no modification to existing platforms, making deployment much more simpler. From the user's perspective, there is still a single service interface. User provide the service along with its equivalent implementations, and internally ScaleWave handles the heavy lifting of mapping services to multiple implementations, grouping them logically, and treating each implementation as an independent service function. ScaleWave also monitors system conditions and routes traffic to the implementation that currently has the least resource bottleneck and provides the most performance gains. ScaleWave operates in two phases, offline phase and the online phase. In the offline phase, developers submit a configuration file containing the service and its implementation. Then the service manager creates logical function groups for each of the service, assigns a single entry point route, and then distributes incoming requests across grouped functions. This prepares the system for the runtime orchestration and leads to this online phase, where in the online phase, as request arrives, the observer component periodically monitors runtime metrics such as throughput, latency, and resource uses. It computes a performance metric defined as the ratio of throughput to the average latency. If the performance drops, the observer triggers the optimizer component, which calculates new replica limits and new traffic distribution values, which are fed to the route handler, which then applies the updated distribution across the implementations. The underlying autoscaler remains completely unaware of ScaleWave, but it reacts naturally to the traffic patterns generated by ScaleWave. Replica counts and the traffic distribution are computed using an online optimization strategy where the goal is to maximize the normalized performance, which is defined by the ratio of throughput to average latency. The optimization is based on a new variant of the knapsack, which we call demand-based dynamic knapsack. Traditional knapsack approaches optimize for the maximum theoretical capacity, which is it maximizes for the resource utilizer, which performs poorly under small or fluctuating workloads. ScaleWave instead introduces a demand constraint considering the current in-flight requests. This allows the system to choose implementations that perform best under current demand conditions. More details can be found in the paper. From a developer's perspective, using ScaleWave is simple. Developers provide implementations as container images using a JSON configuration file. If an implementation requires specialized hardware such as GPU, it can be tagged using the resource key. The ScaleWave then automatically integrates this implementation for further orchestration. To evaluate ScaleWave, we deployed it on a micro-OS cluster consisting of one manager node and three heterogeneous worker nodes, where the workers varied in architecture such as x86 and ARM, and hardware resources such as CPU and GPU. Our test application was the same face recognition service with three implementations: cloud offloading using the network resource, local compute using CPU or GPU, and hybrid processing combined local compute and the cloud offload. Workload tests were derived from a real is telecom dataset, and we also tested in different concurrency levels denoted by C, ranging from 18 to 70. The results show that ScaleWave significantly improves performance. Under high concurrency, ScaleWave served more requests, achieve up to 2 times more higher throughput, and compared to other baselines which show a strong trade-off between throughput and latency, ScaleWave maintained average end-to-end latency below 50 seconds, achieving a good balance. This is due to the ScaleWave optimizing normalized performance rather than the throughput alone. In terms of the normalized performance, ScaleWave improved the performance by up to 42% compared to baseline approaches. And baseline approaches system experienced timeouts of 300 seconds as the load increased. In contrast, ScaleWave smoothly shifted traffic across implemented the different implementations and reduced tail latency by up to 50 to 85%. ScaleWave also improves the cluster resource utilization by which it achieves all these different gains, and the average cluster utilization reached above 78%, which is significantly higher than the baseline configuration. This demonstrates that decoupling implementation from specific resource type allows systems to exploit underutilized resource at the resource concern edge. All these gains come with minimal overhead. The critical components such as routing and optimization introduce less than 1% latency overhead while consuming negligible CPU and memory resources at runtime. To summarize, the scalability challenge at the edge arises from the tight coupling between application implementation and specific resources. Current serverless platform lacks support for scaling multiple implementation with different resource profiles, and ScaleWave addresses this by enabling native support for multiple equivalent implementations, providing systematic orchestration across them, and proactively distributing the traffic across these implementations. ScaleWave works with existing serverless platforms without any modification required, and our experiment shows that ScaleWave is able to achieve up to 2 times throughput improvement and up to 42% performance improvement. Overall, ScaleWave enables scalable applications in resource-constrained edge environments by efficiently utilizing available resource while maintaining platform compatibility and minimal developer burden. Thank you.